In this video, I'm going to look at forces on inclined planes and what is produced. Here are some of them that we're going to learn about today. And before I go further, I want to go back to a question from the last section because it does involve inclined planes. And when you lift an inclined plane, what I want you to see is the force down the hill increases. That's this red arrow. At the same time, the force of friction, because it's not moving down the hill, is increasing until motion first occurs. When the force down the hill is slightly, once again, it just gets to the force of friction up the hill, that friction goes from static friction to kinetic friction, and moving friction is always less. So the down the hill force always will stay the same because it caused the motion in the first place because of the angle of the hill. But the frictional force decreases all of a sudden once it goes from static to kinetic, creating a net force and therefore creating an acceleration. So it's an acceleration, not just motion. You might think this is the right answer, but the better answer is that it's not just moving, but it's accelerating while it's moving down the hill. Okay, so let's look at the forces. First of all, watch out. This is the one I had trouble with when I was going through school early, and that's weight. Weight is always going to be the largest vector straight down. If weight's not your largest vector, you drew this triangle wrong. It's very easy to draw a triangle like this, and then the force into the hill would be longer. That's going to be incorrect. So watch out. Do that check. Make sure the weight is, first of all, straight down, and it's longer than any other vector. So always going to be straight down and longest. That's going to be a key to you being successful at these problems. Next is all the forces caused by this weight. Once you have this weight pushing down into the earth, you now have a force pushing into the hill. And we call that, this right here is going to be your perpendicular force, force into the hill. Next, we have our parallel force. And as it's going into the hill, it's also going down the hill. Once again, caused by weight, so we're going to do SOHCAHTOA to figure out these sides. Force parallel to the hill is also the force down the hill. These are the same things. And the force into the hill, you don't have a block accelerating through the hill, so therefore there must be a force back up. Well, notice this normal force we've seen before, but we no longer have a horizontal surface, so it's not going to be equal to weight anymore. It's going to be equal to this. It's going to be equal to the perpendicular force going into the hill. So watch out for that too. Don't go back to what you did before on an incline. It's going to be this side will be equal to that. And then force of friction. When there's a force down the hill, there's also going to be a force back up the hill. Opposite of motion, because motion would occur, or what motion would occur, because if it's static friction, it's not occurring, but it would occur down the hill, and therefore the force of friction would be up the hill. And then lastly, the angle of incline will always be this angle closest to your box or whatever you drew. If you drew a picture like this, it'd be the one closest to the actual incline, the actual plane of the incline. So let's look at how to deal with some of these, but I'm going to go ahead and show you some shortcuts. Once again, you're probably going to go and use your SOHCAHTOA. Sine of the angle equals opposite over the hypotenuse. Cosine of the angle equals adjacent over the hypotenuse. So just to write these out, well, if I'm solving for the adjacent side and I have my hypotenuse, because we'll usually start these by solving for weight, adjacent and hypotenuse leads you to cosine. And when you rearrange that, adjacent equals cosine angle times hypotenuse. And the adjacent is the force down the hill, so it's rearranged and it's written right here. Same thing kind of goes, but a different side. Force down the hill. So the force down the hill is nothing more than the opposite. The opposite, when I have the hypotenuse, is going to lead me to the sine function. When I rearrange this and move the hypotenuse over by multiplying it out, you get sine angle times the hypotenuse. And then just remember, when I do solve for this, I actually solve for the normal force. Just it's up out of the hill instead of into the hill. Okay, so let's walk through this problem. How much would a 1.5 kilogram block accelerate down a 15-degree frictionless inclined plane? So when I approach this problem, first thing you want to do is you want to draw the picture, draw the incline just like this, throw a box or something in there, no matter what it is, if it's a car or whatever rolling down the hill. And it's the frictionless plane, which is going to be important because I'm not going to include friction in here. So the force, when it's frictionless, if you ever see this, once you figure out the force down the hill, you pretty much have, and you know your normal force, actually not normal force here because there's no friction, and you know your mass, you're ready to go ahead and solve for it. But a lot of times you're given mass, and in order to draw these and start everything out, you're going to have to figure out the weight in the first place. So you're going to use that to find weight, and then you can solve for every other side. Let's take a look at what I mean. Weight's down longest vector. It's our hypotenuse. The adjacent, the the perpendicular force is into the hill, and that's your adjacent side of the triangle that we're forming. Down the hill is the opposite side, also written here, so I can actually see what's happening, because this is what I'm going to consider when I'm looking at net force. Normal force should equal that force into the hill, and no friction in this problem. So let's start by solving for weight. Fw equals mg, so we have our 1.5 right there. We're going to use 10 meters per second squared as our gravity. When we do that, we get a weight of 15 newtons down, and now you have something to plug into this 15 newtons. You now have a side. Our first side is going to be our hypotenuse. You'll start most problems like this. They might be nice and give you the weight. If they give you the weight, you're probably going to have to go ahead and solve for mass later on, because you're going to need that to figure out the acceleration. So depending on where they start you, you're going to be using this weight equation probably a lot. Okay, so now we're going to solve for, and I kind of showed you the math earlier, we're going to solve for our force down the hill, and this one I start with down the hill, and just note that it's the opposite side. There's my math, that gets you to that, and so when I solve for my opposite, I now have that force down the hill. I'm going to use the sine of 15 degrees. Once again, that angle is the same as that angle. 15 newtons was my weight that I solved for. That's my hypotenuse. So I'm pretty much doing this right here. And once I solve for that, type it in the calculator. Watch out, if you are in radians, you're not going to get this answered, so switch it to radians. But if you're in degrees, you should get 3.88 newtons. And that's going to be the force down the hill that's going to be creating this acceleration. So at this point in time, these are canceling off. This and this are going to cancel off. And the only force, weight, I don't have to consider weight anymore, because weight is what caused all these other vectors. So I actually took care of weight. Once I found these other forces, I was done with weight. I'm not going to use weight again. I'm going to use anything else that's going on. Well, with no friction, we're only going to have the force down the hill going into the acceleration. So this is going to be my net force that I'm going to use in the F equals ma equation. When I rearrange that, A equals, so I divide out the M, I divide out the M, A equals F over M. And I get 3.88. I go back to get my mass. I had mass from earlier, and I get 2.59 meters per second squared. Okay, so now what if there was friction? So let's go ahead and start back. If there was friction, I already have this all. You want to start off by thinking, okay, if there is friction, let's go ahead. What is it? Oh, here we have a wood and wood. Wood and wood, so this is going to be important. We're looking at wood and wood, and sometimes you'll have like a list. You need to figure out what two objects are rubbing together. We have our force down the hill we found before. But now we want to find the force of friction. In order to find the force of friction, remember the force of friction equation is you need two things. You need the normal force and you need the coefficient of friction. So in order to find the force of friction, I'm going to go ahead and find the force into the hill. And so I'm going to go ahead and do this to find the force into the hill. And it's going to be, the force into the hill is going to be the adjacent side, so it's going to be a cosine. And it's going to be cosine times the hypotenuse, which is the weight, and that's what gets us to this. So cosine of 15 times the 15, once again, if you're in degrees, is going to give you 14.49. So that's our force that's going to be into the hill. Well, that's the same force. This is going to be into the hill. This right here, once again, they are vectors. So the normal force is going to be force up out of the hill. And this is the normal force that I'm going to use in my force of friction equation. And then here I'm saying how much would a block accelerate? Okay, so what I'm doing here is I'm just doing a check. Because if there's not enough force down the hill, it's not going to start in the first place. So you might think this is pointless and not do this, but then if the block doesn't move in the first place, you're never going to get to the actual second step. You would stop here and say, no, it just doesn't move. So I'm doing my check. I'm going to go ahead, and here it says how much would it accelerate? Well, let's make sure it accelerates in the first place. So before it would ever move, it has to pass up this maximum. So it has to pass up the force of static friction. So 0.25, and we're going to use our normal force from up here, and we find out that 3.62 newtons is our force backwards. Well, our down the hill is 3.88. Our force up the hill would have been 3.62. So therefore, this one does win out, and so there would be acceleration going on. Well, this is pretty much, after this point, we're not going to use this number because it's going to be moving. So we need to figure out our kinetic friction. Let's find out what is actually, what's the new friction while it's moving to find out what it's actually accelerating at. So we go back and we take our 3.88 from before, but now we're going to go ahead and we're going to take our kinetic friction, which will always be less than static friction, and for all the problems we do. And that's going to be 0.20 times that 14.49. And so we get a force friction of 2.90. Well, that 2.90 is the force back. And we have our force back right here, our force of friction. We have that 3.88 newtons going down the hill. And so now we have to figure out our net force. So we take these two into account, our force down the hill minus our force up the hill. I'm calling my positive my down the hill. And I get a 0.98 newtons down the hill. So this is the actual net force that's going to go into acceleration. And then we go to our acceleration equation. F equals ma rearranges to A equals F over m. So 0.98, it's the same block from before that was 1.5 kilograms. So I'm pulling this from the last problem. And we get an acceleration down the hill of 0.65 meters per second squared. And so that's kind of how you'd approach this. A lot of curveballs they can throw at you in questions, but this is the basic kind of problem you do. Often there's going to be like a second part to it. So let's go ahead and take this acceleration, 0.65 meters per second squared. There's your acceleration. How fast would the block be moving? Df equals question mark. After 3 seconds, so there's going to be 3 seconds. And if you don't hear otherwise, you're going to have a VI of 0. So here you're starting from rest. So how fast is it going 3 seconds after it started moving? And we look for our equation A, VF, T, and VI. A, VF, T, and VI right there. We're going to use that equation a lot. So VF equals VI, which is 0, plus A, which is 0.65, times T, which is 3. And so we plug that in, 0.65 times 3, and we get 1.95 meters per second. So you may have a lot of different end problems, side questions, things like that. Some of you in honors will see, or just depending on college, whatever class you're in, you're going to see you see a bunch of pulleys and other things attached to this. If I get time, I'll go ahead and make more videos later on.